So, are you tired of wrestling with internal bore finishing that maybe just isn't quite up to scratch?
Yeah, getting those results consistent can be tough.
Right. And maybe manual methods are, well, they're inconsistent, they eat up your time, and you end up with a pile of rework.
Happens all the time. Frustrating.
Okay, let's unpack this then, because today we're doing a deep dive into CNC internal grinding machines.
Ah, yes, the automated precision solution. It really can make a huge difference in quality and, frankly, efficiency.
Exactly. So, what is it fundamentally?
Well, basically, it's a specialized machine.
Hmm.
It uses computer-smart CNC, computer numerical control, to guide a very fast spinning grinding wheel.
Okay.
And it guides it with incredible accuracy inside a workpiece. The whole point is removing material precisely to get these really smooth, dimensionally perfect internal surfaces.
And I guess looking at one, it can seem pretty complex, lots of moving parts.
Oh, definitely. But understanding those core elements, how they work together, that's how you really grasp its potential.
It's seeing how each bit contributes to hitting those precision levels that, let's be honest, are just impossible manually.
Absolutely. It's the synergy, really. Each component has a vital role in getting that ultimate accuracy for internal finishing.
Okay, so let's maybe peel back the layers a bit. What are the key players here?
Right. Well, you got the foundation, the machine bed, super important.
The bedrock. Yeah,
Then the workhead, sometimes called the headstock, that holds and spins the part.
gotcha.
Then the wheel head, that's where the spindle and the grinding wheel itself live.
The business end.
Kind of, yeah. And don't forget the dressing device, crucial bit of kit, and obviously the CNC control system, the brain.
The brain orchestrating it all. Okay, let's start with the bed. You said foundation.
Exactly. It's engineered to be incredibly rigid. Its main job, apart from holding everything, is absorbing vibrations.
Even tiny ones.
Oh, especially tiny ones. Because when you're grinding internally to micron tolerances, even microscopic movements mess things up. They show up on the surface.
Right. Makes sense. And the work table sits on that for the fixtures.
Yep. Securely fastening your workpiece holders, that happens right there on the table, on the bed.
Okay. Then the workhead or headstock that's doing the holding.
That's right. Grips the workpiece firmly,
Mm.
usually uses chucks or maybe some custom fixtures depending on the part.
Mm-hmm.
And critically, it controls the rotation speed of the part very precisely.
And I've seen sometimes there's a tailstock.
Yeah, exactly. For longer parts, more slender ones, that might flex. The tailstock gives extra support at the other end, keeps everything stable.
Right. Stability is key. Okay, wheelhead next.
Wheelhead, this is where the actual material removal happens. It houses a high-speed spindle.
High speed, like how fast are we talking?
Oh, it can be very fast. Tens of thousands of RPM sometimes, especially for small wheels. And that spindle spins the grinding wheel.
The abrasive wheel, the cutting tool.
Precisely. And these wheels aren't generic. They're made from specific abrasive materials chosen carefully based on what you're grinding.
Right. Depends on the workpiece material.
Exactly. And what's interesting is the wheel head itself moves. Very precisely, in straight lines, obviously.
To feed into the bore.
Yes, axially or radially. And sometimes it can even rotate on another axis, usually called the B-axis,
Oh, why would it need to rotate?
for grinding tapers or complex internal shapes, not just straight cylinders. It lets the wheel approach the surface at different angles.
Ah, okay.
Yeah.
Very clever. Now, you mentioned the dressing device. That sounded important, but maybe less obvious.
Absolutely critical. It's this ingenious little system, usually uses a very hard tool, often diamond,
Diamond. Okay.
and its job is basically to give the grinding wheel a refresh. It reshapes it slightly, sharpens it by knocking off worn abrasive grains,
Ah, like truing it up.
exactly like truing it up, but also cleaning out any tiny bits of workpiece material that might get embedded in the wheel.
Clogging it up.
Right. So dressing keeps the wheel cutting consistently, maintains its profile, and that's vital for getting that top quality surface finish and holding tolerance part after part.
Makes sense. Without it, the wheel just gets dull and loaded.
Performance would drop off very quickly.
Yeah.
You lose precision, finish quality would suffer.
Yeah. Okay.
Yeah.
And tying it all together, the CNC control, the brain.
The brain, the central nervous system. It takes all the programmed instructions, the G code usually, and it perfectly coordinates every single movement.
Everything.
Everything. Workhead rotation, wheel head position, and feed rate.
Yeah.
When the coolant turns on and off, when the dressing cycle happens.
Wow.
It's this incredibly detailed, automated coordination that lets you hit that micron level accuracy. We're talking tolerances smaller than a hair's width consistently.
Which you just couldn't do by hand.
No way. Not reliably, not efficiently.
Okay, so if you're facing these internal finishing issues, you might look around and see, well, Surface grinders, cylindrical grinders, centerless ones. It gets confusing.
It really can.
Yeah.
And, choosing the wrong tool for the job, that can set you back. Wasted time, scrap material, costs add up.
So what is it about the internal grinder that makes it the right choice for, well, internal surfaces?
It really comes down to its fundamental design. It's built from the ground up for that specific task.
Unlike the others.
Right. While other grinders are engineered for flat surfaces or external round shapes, the internal grinder is specifically designed to get inside the part and work on those inner diameters. Bores, basically.
Okay, so let's clarify those differences maybe. Surface grinders first.
Sure. Surface grinders think flat. Their job is making flat surfaces, like the top of an engine block, or maybe cutting precise grooves or slots into a flat surface.
Makes sense. Cylindrical grinders.
As the name suggests, they handle external round shapes, grinding the outside diameter of a shaft, for instance.
Okay. And centerless. That sounds a bit different.
It is.
Yep.
Centerless grinders are workhorses for high-volume production of external cylindrical parts. Think pins, rollers. And they do it without clamping the part in a chuck or between centers.
How does that work then?
It's clever. The workpiece rests on a little blade between the main grinding wheel and a second, slower regulating wheel. This regulating wheel controls the part's rotation and feeds it through. Very efficient for the right kind of part.
Interesting. So the working principles are quite distinct then.
Very. With internal grinding, your workpiece rotates, and a relatively small grinding wheel, spinning really fast, feeds inside the part, either along its lengths or straight in.
Right. Inside job.
Whereas a surface grinder, typically the workpiece moves back and forth under the grinding wheel, or the wheel moves over the workpiece, using its edge or face to create that flat plane.
Okay. And cylindrical.
Cylindrical grinders usually hold the workpiece between centers, or in a chuck, rotate it, and then the grinding wheel moves in radially or traverses along the lengths to grind the outside diameter.
Got it. So the workpiece types are pretty specialized too.
Definitely. Internal grinders, internal bores, internal tapers, complex internal shapes like bearing raceways, that's their specialty.
Surface grinders.
Flat stuff. Parallel surfaces, stepped surfaces, grooves, guideways on machine tools, things like that.
Centerless.
High-volume external cylinders, maybe simple tapers. Think lots of identical round parts.
And cylindrical covers?
A broader range of external shapes. Basic cylinders and tapers, yes, but also shoulders, faces, and more complex external forms like you find on camshafts or crankshafts.
So if we had to boil it down, the core difference for CNC internal grinders is
Simple. They process internal surfaces. That's their unique purpose.
their domain.
Precisely. Now, you might also hear about jig grinders, worth a quick mention.
Yeah, what's the difference there? They sound like they do precise holes too.
They do. They're incredibly precise machines. But their focus is often more on, say, contouring complex shapes, especially in tool and die making, grinding precise location holes or intricate profiles.
So less about the pure surface finish on a simple bore, maybe?
Generally, yes. A dedicated CNC internal grinder is really optimized for achieving that specific internal roundness, straightness, and surface finish, often in a production setting, which might be different from the typical applications of a jig grinder.
Okay. So internal grinders really are the masters of the inner domain, as one source put it.
That sums it up well. They're engineered specifically for the challenges of grinding inside a part accurately and efficiently.
Right. Now, for a lot of listeners, the big question is probably how? How do these machines get those super tight tolerances and that almost mirror finish inside a bore?
Yeah, because manual methods often just can't cut it, or they're incredibly difficult and inconsistent.
Exactly. So what are the secrets? Is it just the CNC?
The CNC is huge, but it's really a combination of things working together perfectly.
Okay.
You got that super rigid machine construction we talked about, minimizing vibration.
Right.
You've got the ultra-precise CNC control itself. Then the specialized grinding wheels, small ones designed for internal work. Optimized grinding parameters, speeds, feeds, depths of cut. Very important. Effective cooling is essential. And that regular automated wheel dressing we discussed.
A whole package deal.
It really is. Take the CNC control again. Its ability to execute the program path, speed, and feed rate with extreme precision over and over again. That gives you consistency manual operation just dreams of.
Repeatability.
Exactly. And it's smart too. Modern CNCs can often compensate for tiny amounts of wheel wear automatically as the grinding happens.
Keeping it accurate even as the wheel wears down slightly.
Yes, within limits, of course. But it helps maintain tolerance over the entire cycle.
Okay. And the wheel itself? You mentioned specialized abrasives.
Right. It's not just any grit. You choose the abrasive, maybe aluminum oxide, silicon carbide, or super abrasives like CBN or diamond, based specifically on the workpiece material. Hardened steel needs something different than ceramic, for example.
And the grit size matters for finish.
Absolutely.
Right.
For those really smooth finishes, we're talking surface roughness, potentially below 1 micrometer RAW, which is incredibly smooth.
Millionths of a meter smooth.
Pretty much. You typically use finer grit wheels for the final finishing passes.
Makes sense. Coarser for roughing, finer for finishing.
That's the usual strategy.
Yeah.
And the CNC maintaining consistent spindle speeds and feed rates is also vital.
Why consistent?
If the speed of feed varies unexpectedly, you can get uneven material removal. That leads to chatter marks, poor finish, maybe inaccuracies. Uniformity is key.
And you mentioned high spindle speeds are common.
Yes, especially with small diameter wheels needed for small bores, you need high RPMs to get the necessary surface speed at the grinding point for efficient cutting.
Okay. And coolant. More than just keeping things cool.
Oh, much more. Cooling is critical. Yes, prevents thermal damage, maintains dimensional stability. But the coolant, or lubricant, also drastically reduces friction between the wheel and the part.
Better cutting action.
Better cutting, less force needed, and crucially, it flushes away the grinding debris, the swarf.
Gets the tiny chips out of the way.
Exactly. If that swarf builds up, it can get dragged around and scratch the surface you just finished grinding. So effective flushing is essential for a good finish.
Right. Don't want to damage the perfect surface you just made.
Precisely. And that brings us back to automatic wheel dressing again.
The game changer for consistency.
Absolutely. Especially in production runs. The CNC triggers the dressing device at programmed intervals, reshapes the wheel, resharpens it.
So the wheel is always cutting optimally.
Pretty much. It ensures the wheel profile is correct, maintains its cutting efficiency. That automation is key for hitting tight tolerances and getting that consistent surface finish part after part without operator intervention every few minutes.
Okay, that paints a clear picture of how the precision is achieved. Now, the next logical question is, what kind of parts is this actually good for?
Yeah, a really important question. Because you don't want to use the wrong process. Is internal grinding the right fit for your specific components?
Right. What are the ideal candidates?
Well, fundamentally, any workpiece that needs a precise internal feature. Could be a straight cylindrical bore, could be tapered, could even be a complex internal shape. But the key requirements are usually tight dimensional tolerances and a fine surface finish.
Okay. Can you give some specific examples?
Sure, think about bearing races. That inner track where the balls or rollers run, its roundness and surface finish are absolutely vital for the bearing to work properly and last a long time. Internal grinding nails that.
Makes sense. High precision needed there.
Definitely. Or think about hydraulic cylinders and valve bodies. They need precisely ground bores for seals to work effectively, for pistons or spools to move smoothly without leaking.
Sealing and smooth operation. Got it.
In the automotive world, lots of critical engine components. Things like cylinder liners, the big end bores of connecting rods, piston pin bores, they all have incredibly tight tolerances. Internal grinding is often the only way.
Demanding applications.
Very. Also, gear shafts sometimes need internal sklines ground, or maybe just a very precise bore for mounting something else accurately. And things like industrial nozzles or flees. The internal profile can directly affect fluid flow or wear resistance, so getting that shape and finish just right is crucial.
Affects performance directly.
Exactly. And even in the medical field, some surgical instrument parts or components for implants need the kind of high precision and specific, often very smooth, biocompatible finishes that internal grinding delivers.
Wow, quite a range. What about materials? Is it just steel?
Oh no.
No.
It's very common for hardened steels, yes, and high-strength alloys like stainless or inconel. But CNC internal grinding is versatile. You'll see it used on ceramics, tungsten carbide,
Really hard stuff, yeah?
and even things like optical glass for very specialized high-precision applications. The right machine setup, the right wheel, it can handle a surprising range.
So the takeaway is, if your part has an inside diameter that needs to be perfectly round or perfectly straight or have a precise taper,
Or even a complex internal profile.
and it needs tight tolerances and a great finish.
Then CNC internal grinding is very likely the best solution. Often it's the only way to achieve those results efficiently and accurately.
Okay, so let's try and wrap this up. The main point here is that CNC internal grinding machines are really essential tools for high-precision internal bore finishing.
Absolutely. They deliver exceptional accuracy, top-notch surface quality, and that all-important repeatability you just don't get manually.
And the impact of that.
Well, boosts productivity, ensures the quality of really critical components, and you see that across so many demanding industries: aerospace, automotive, medical, hydraulics, bearings. The list goes on.
So maybe a final thought for our listeners. As you think about your own manufacturing challenges, particularly those tricky internal features,
Maybe ask yourself, what new possibilities could this kind of internal precision unlock?
right? What internal shapes or tolerances might you have thought were just too difficult or maybe even impossible before?
Exactly. Could achieving that level of accuracy and finish internally open up new designs or improve existing products? Definitely something worth mulling over.